So you are the network administrator for a big company, and you just got a call that this individual's machine is not working, and this was his reaction after his computer's not working. So check it out. Tell me what you think. Watch this guy right here. Uh oh. Uh oh. Oh boy. We are putting the monitor on the printer, and this printer is not working. The copy is not working. As you can see, folks, he's very, very upset. Even this lady right here jumps out of the way. Okay. All right. So you may come across people like that, and that's unfortunate. Ladies and gentlemen, welcome to Module 3, Protocols and Models. So more than likely, maybe the protocols were a little messed up on that computer, maybe, because he was trying to print to it and it just wasn't working. Maybe. I don't know. Who knows? That guy was very, very upset. So we're going to get into this protocols and modules. Okay. Models, excuse me. In this, we're going to talk about the rules. I'm going to describe the type of rules that are necessary to successfully communicate. We're talking about protocols. Protocols are very, very important. We're going to talk about the bubble for a quick second here. Protocol suite, explain the purpose of adhering to protocol suite. Standards organizations, explain the role of standard organizations in establishing protocols for network interoperability. Explain the TCP/IP model versus the OSI model. Please do not throw sausage pizza away. Email me the acronym I just used right there. Data encapsulation. I really like this one. This, when we talk about data encapsulations, that is that piece of mail that gets put inside of an envelope and it gets housed and addressed and put into the mailbox. We're going to go back to that mail truck. And then data access. Explain how local hosts access local resources on the internet. All right. Okay, we're going to kind of pass this up here. All right, so the rules. Before we get into the rules, we're going to watch this video. We're going to watch this video on the rules. So pay attention to this video, and we're going to kind of break this video down here. So here we go.
This is how we see the network. Using topology diagrams, we can see the devices in the network, including end devices, such as desktops and servers, and intermediary devices, such as switches and routers. These diagrams may also contain detailed information about a device, such as the MAC address of the Ethernet and wireless NICs, IP or Internet Protocol address information, default gateway addresses, and addresses for the DNS server. By the way, don't worry about what these terms and addresses mean right now. All of this will be explained throughout this course. This is how we see the network. But how do devices see the network? You can think of it as every device being in its own bubble. The only thing a device knows is its own addressing information.
Okay, I'm going to stop the video right there for a quick second because that's a very, very good point in this video. The only thing the device knows is its own addressing information. Okay, very important. Its own addressing information. So I'm going to go back to this picture that I showed you in a previous video. Okay, so take a look at this picture again. This is this cul-de-sac, right? This is this house, these homes on this cul-de-sac. They're all part of the same subnet. You guys remember that? Because they're all on the same street. So they all share the same street, right? There's a mailbox right here. The mail truck comes in, all that good stuff. However, each house, okay, is going to have its own protocol, although very similar protocols might be the same, okay? But each one of these houses are going to do things different. Very similar to, hey, I need you to take out the trash. Okay. This house may take out the trash going through a certain garage, or they may take the trash out going through the back, or they may take the trash going out through the front. You know, whatever that protocol may be, they're probably very, very similar. Okay. Very similar as far as how they see each other in the bubble. However, going back to this bubble situation here, they only know what to do when things happen, right? When it's time to take out the trash, that's when those protocols happen. So in these particular houses, there may be some teenagers, hey, you need to go take the trash out right now, something like that. I don't know. Whatever the protocols may be inside that house, right? And that's kind of where we're at there. Whatever that protocols may be, and they need to act on it, right? They need to act. So let's continue the video.
In other words, this is how a device sees the network. It doesn't. So, how does a device know its IP address and what network it belongs to? How does a device know if the destination device that it needs to send information to is on the same network or another network? If the destination is on another network and the information has to travel through intermediary devices, how does the source device know where to send it next? How does the source device...
Okay, I'm going to stop the video again really quick. And here's your in-class question. Just go through this really quick. Let's see here. So you just got a call that, this is just a hypothetical, you got a call that a customer's computer is not working. And you pull up this following information right here. And the computer is not working. I want you to email me and tell me why you think
device
that is.
know if the information it sent was received or if it needs to resend anything that might not have reached the destination. The answer to all of these questions is protocols, the rules that govern how devices communicate. Most network communications are broken up into smaller data units, which we can refer to as packets. When packets are sent on a network, many protocols are involved to help them reach their final destination, each accomplishing a different task. There are protocols such as Ethernet and wireless protocols that physically connect the device to the network. The protocols DHCP and ICMPv6 provide IP addressing information, including IP addressing that tells the device what network it belongs to, the address of the default gateway that tells the device where to send packets that are destined for another network, and the address of the DNS server for when a device knows the domain name of a destination but needs the destination's IP address.
All right, I want to stop the video for a quick second because you see this word default gateway, okay? Default gateway. Every single time you hear the word default gateway, I want you to think of this item right here. This is a mail truck, and it's designed to take your mail and take it to a post office and send it out wherever it needs to go. So the reason why I bring that up as far as the default gateway, because the truck is designed to move your mail, right? It's designed to, its protocol is to get your mail and take it out, and it's designed to pick up items like these, right? Let's see, let me show that picture here. It's designed to take these type of items, right? These letters and mails. So very essentially the same thing. You send this letter in the mail, okay? Or like a email, right? If you send this letter in the mail, its default gateway is you're going to hit the mailbox and the mail truck's going to come pick that up and haul it off. Very similar to how email works. It's going to have a default gateway in order to send out the information. Let's continue here.
For instance, when a user requests a web page from a web server, such as www.example.com, the device asks the DNS server for the IP address of the domain name www.example.com. IP is used to deliver the packet from the source of the information to its final destination, in this case the web server, similar to sending a letter. The web server will then respond back with the requested web page. TCP is a protocol used to guarantee reliability. In other words, to make sure all the information that was sent was received, such as the information that makes up the requested web page. If any of the IP packets don't make it to the destination, TCP resends them. So although we see the network like this, remember, it's a combination of many different protocols that allow devices to really see their place in the network and how to communicate with other devices.
All right. So hope you guys understand that, because that's a very key point, right? So that's when it comes to the rules, right? Protocols. Everything typically has protocols. Machines should have protocols. It should know what to do when an action happens within the machine. Very similar to, like I told you with this graphic, and I got to keep coming back to it. Got to come back to it again. You're living in these homes, right? We're always gonna refer to networking in real life here. So you're living in these houses, and something needs to happen inside these homes, and these homes are going to have protocols in order for them to operate correctly. Okay, so continuing here. Okay, we just watched a video. Now, networks can vary in size and complexity. It is not enough to have a connection. Devices must agree on how to communicate, right? They need to know how to do these. So there will be a source, there will be a destination receiver, and there will be a channel media that provides the path of communication. That's that network media. So if you go back to my module 2, that's that basic switching configurations, right? All communications are governed by protocols. These are the rules. Protocols are the rules that communications will follow. These rules will vary depending upon the protocol. Individuals must use established rules or arguments to govern their conversations. The first message is difficult to read. So take a look at this. It says, let's look at the first one. It says, humans communications between governed rules. It is very difficult to understand messages that are not correctly formatted, do not. So essentially it's showing two messages. One of them is formatted correctly, the other one is not. So it is rather difficult to see these two, right? Well, one of them you can see very, very well. The other one is a little funky Comedina, right? Little funky. Protocols must account for the following requirements: an identified sender or receiver, common language and grammar, speed and timely delivery, and confirmation of knowledge and agreements. Okay, requirements. Let's go back to this. Identify sender and receiver. Okay, so watch this, and I'm going to bring it up again. It says identified sender and receiver. Folks, what do we have here? What do we have here again? We have our wonderful letter. Identify sender and receiver. Here's our receiver. Here is the sender. Very similar to a mail, sending out mail. Here's the sender, and here is the receiver of that, right? Very, very important there. Network protocol requirements. Common computer protocols must be in agreement and include the following requirements: message encoding, message formatting, encapsulation, message size, message timing, and message delivery options. Message encoding. Encoding is a process of converting information into another acceptable form of transmission. Decoding reverses the process to interpret the information. So essentially, the message source, the message source encodes the information, right? Those ones and zeros, transmits it, goes over that physical medium. This could be that Ethernet cable, that fiber optics. It receives it and decodes it, and then it gets to its destination. Now, message formatting. Oh, pretty cool. Look what we see here. This is our mail that I've been referring to a lot. When a message is sent, it must use a specific format or structure. Message formats depends on the type of message and that the channel that is used to deliver the message. So, looking at this graphic, as you can see, this is a piece of mail. It has the recipient on there. It has the sender, as we've been talking about. And inside the mail, there is an actual message. There is a message. So, I really like this graphic, and I'm going to pull out my pen here because I think this is awesome. So, in looking at this, when we're looking at the message encapsulation, our destination address, there it is. That's how that relates. The source IP, that would be related to here. This is where it comes from. And then all the content inside of that mail, right? All the contents inside of that mail have to deal with all of these items inside of a packet. And this is a very good graphic. I love this because it definitely shows how this works in the real world, right? Now, before that, let me ask you a question. What would be the item used to deliver this? What type of media could deliver something like this to your computer? Send me an email on that one too. Message size. Encoding between hosts must be an appropriate format for the medium. Messages sent across the network are converted into bits, right? Those are those ones and zeros. The bits are encoded into pattern of light, sounds, or electrical impulses. The destination host must decode the signals to interpret the message. So I thought this was pretty cool. Check this out. It must decode the signals. Watch this. Let's see here. Oop, there's a light on and off. Folks, this is a good representation of what that physical medium sees, right? These are these lights encoding and decoding information. Either the light is on or off. Let's watch it again. See the light coming on and off? Right? Those are those impulses. Those are those light. Those are all those lights that those physical mediums they see when that data gets sent across the network. Message timing, flow control, manages the rate of data transmission, defines how much information can be sent, and the speed at which it can be delivered. Interesting. Response timeout manages how long a device waits when it does not hear a reply from the destination. So, have you ever waited on somebody and somebody was supposed to show up with a package and they said they were coming? They said they were supposed to be there and they didn't show up. You call them back and say, hey, send it back, man. What's going on? Where you at? Get your butt over here, right? Access method determines when someone can send a message. There may be various rules governing issues like collisions. This is when more than one device sends traffic at the same time and the messages become corrupt. So that's essentially like a highway, like a single lane highway. You got maybe those, you ever come across those construction zones where one person the construction guy has a sign at the end of this street that says stop, and then the other construction guy says slow. So one traffic can come in at the same time, only one at a time. And what happens if both sides say slow and they both come down that road, right? So they end up having a collision, right? We don't want that to happen. Now, message delivery options. Message deliveries may one of the following, oh my gosh. Message delivery options. Message delivery options. Unicast, multicast, and a broadcast. Let's talk about these. So, a unicast. Unicast is one-to-one communications between you and one other person. A multicast is one-to-many. Typically not all, just one-to-many. Like you're only trying to talk to a certain amount of people. A broadcast is, hello, everybody, I'm here. Can everybody hear me? Hello, I'm here. I'm broadcasting to the world that I'm here. So everybody hears what's called a broadcast. So these are the different types of deliveries. Documents may use the node icon typically as a circle to represent all devices. So this is a pretty cool little graphic here. So unicast, as you can see here, let me pull the pen out here again. Unicast is communication between this person and this person. Notice that these are not accessible, right? Because this is only between this sender and that receiver. Now, multicast, essentially, I'm sorry, I should not have done that. That's my fault. A multicast is these individuals see the information. They don't. Broadcast would be that everybody gets it because they're trying to find out who's who, right? That's kind of a technology, a protocol called ARP that we're going to get into. It's called Address Resolution Protocol, where it matches MAC addresses to your IP addresses. So, this is a broadcast where everybody gets the information. It's trying to figure out who is who. And let me go back to my graphic again, because I just love this graphic. So the mail truck comes in, and he shows up at your mailbox, but there's no address information on there. It just knows that it's on this street. So if the mail guy knows that the mail needs to be delivered on the street, what might he do? He may broadcast to every single house, "Hey, are you such and such?" That way everybody knows, like, "Hey, the mail truck guy came." Right? That would be a good example of a broadcast. All right, let's get into protocols. Network protocol overview. Network protocol is defined as a common set of rules. We've already been kind of getting into this. Protocols are a set of rules. Can be implemented in software, hardware, and both. Protocols have their own function, format, and rules. As we can see with network communications, enable two or more devices to communicate over one network. Network security, secure data, provide authentication, data integrity, and data encryption. That's that CIA triad we talk about all the time in cybersecurity. Routing enables routers to exchange route information, compare both information, select best path. And service discovery, use the automatic detection to devices and services, automatic detection. Now, network protocol functions. Devices users agreed upon protocols to communicate. Protocols may have one or more functions. Addressing, identifies sender and receiver. That's that mail. Identifies sender and receiver. As you can see here, we identify the sender right here, and this is the receiver. Going back to that wonderful piece of mail. Reliability, provides guaranteed delivery. Provides guaranteed delivery. Now, let's go back to the mail truck, our default gateway. Some people would say, "Hey, I don't like USPS. I'd rather use UPS, or I'd rather use FedEx." Depends. Whichever preference may be the best. Reliability. Flow control ensures that data flows in efficient rate. Make sure that everything is good to go, right? There's no collisions or anything of that nature. Sequencing uniquely labels each transmitted segment of data. We're going to kind of talk about that here in just a little bit. Sequencing labels. Error detection determines if the data became corrupted during the transmission. Kind of like if your mail gets damaged inside of a truck, right? We don't want that to happen. Application interfaces, processes to process communications between network applications. Now, protocol interaction. Networks require the use of several protocols. Each protocol has its own function. Now, HTTP, and I'm going to put this number up here really quick because HTTP uses this port number. Uses that port number. I want you to email me which port number uses the HTTPS Send me an email on that one. TCP manages individual conversation, provides guaranteed delivery flow control, okay, transmission control protocol. IP, deliver messages globally from sender to receiver. That's the IP address, Internet Protocol. And Ethernet delivers messages from one NIC to another over the same local area network. Protocol suites. A group of interrelated protocols necessary to perform a communication or function. A set of rules that work together to help solve a problem. A set of rules that work together. Set of rules. The protocols are viewed in terms of layers, higher layers, lower layers, concerned with moving data and providing services to upper layers. So, a set of rules that work together to help solve a problem. I want you to think of this as a big Amazon facility or some big shipping yard or whatever. They all may be tasked with making sure, let's go to Amazon. They may be tasked with making sure that whenever somebody buys anything on Amazon, that everybody has a set of rules, everybody has protocols that need to happen in order for you to get that information, right? In order for you to get that package. So everybody has their own rules and protocols, but they all have to work together. That's the key. They all have to work together. So the TCP IP, OSI, AppleTalk, and Novel NetWare. This is an example of the TCP IP layers. And we're going to get into all of these different little protocols because each layer has its own set of rules. And as I was talking about earlier, this is that Amazon facility, right? And they all have a set of rules that need to happen in order to get the package, right? I'm just going to draw a picture of a package or something. I'm not a very good picture person at all. I don't do pictures all that great. So, but I think you get the idea there. TCP IP protocol example. Network access, internet, transport, and the application layer. So they essentially put all of those in. This is like a protocol stack. They all work together here in the local area network. TCP IP is open standard protocol suite that is freely available to the public and can be used by any vendor. The standards-based protocol suite that is endorsed by the network industry and approved by a standard organization to ensure interoperability. So this is essentially all the different protocols that work within TCP IP, and we will go through a couple of these. At the network layer, we have ARP, Ethernet, wireless local area networks. At the internet layer, we deal with a lot of IP addressing, IP version 4. Here's what you call network address translation. Let me go back. Network address translation, we will get into that in later videos. Messaging, routing protocols, transport layers. This is kind of how that connection is established to transport everything that needs to get there. TCP, hey, do you hear me here? I'm here. UDP, it just kind of sends it and hopes that it gets there, right? It's kind of like throwing a ball out in the middle of the field, hope somebody catches it. And the application layer, this is actually what we see. Most of these items here, we don't see this, but we see the application section of it. TCP IP communication process. This is pretty cool. A web server encapsulates and sending the web client page to a web client. A web client de-encapsulates the web page for the web browser. Take note of the ones and zeros. So everything gets encapsulated. And then those light pulses, right? Those light pulses, as I showed you that little video, it takes that data and decapsulates it so the end user can see it, or that end device can see the information. Standards and organizations. Now, these are some of the standards and organizations that deal with a lot of how your data gets moved, how it needs to get there. These are some internet standards. I'm not going to get through all of these. You can see these on your screen here. More internet standards here. Internet Corporation of Assigned Names of Numbers coordinates IP address allocations and managements of domain names and assignment of other information. The Institute of Electronics Engineers, the IEEE, they call that IEEE. All right, and then let's go to this next one here. Now, reference models. This is pretty cool. Now, the benefits of using a layered model. Now, pull the pen out here again. We've been talking about this one. This is the TCP IP model. Now let's take a look at the OSI model. Now, the best way I can understand the OSI model to learn the different learn the different layers. We have the physical, the data link, the network, the transport, the session, the presentation, and the application layer. So to learn all these, to know them, you still need to understand what they do. But to give you the basics of them, please do not throw sausage pizza away. That's the mnemonic for that. But as you can see here, as it pertains to the OSI model and then the TCP IP model, they all do the same thing. However, they're broken down into different layers. Certain layers do the same thing. Some layers are taking other duties. Like they're doing the same thing, but each layer is kind of different, which is pretty cool. The benefits of using the layered model. Assistant protocol design, because protocols that operate at a specific layer have defined information, right? Foster competition, because products from different vendors can work together. Prevent technology or capability changes in one layer from affecting other layers, and provide a common language to describe the network functions. Now here we go. OSI, the physical layer. This is layer 1. Describes the means to activate, maintain, and deactivate physical connections. That's that physical connection, right? That's that RJ45 connection that gets plugged in to that switch, or that fiber cable that gets plugged in to that router. The data link, the data frames, that's those ones and zeros, light pulses that are showing up as that physical medium is plugged in. The information shows up, that data link, as it makes its way up. Network layer provides exchanges of individual pieces of data over the network. This deals with IP. This is IP information. Defines a transport layer, defines services, segment transfer, reassemble the data for individual communications. The session provides services, presentation layer, and to manage the data exchange. Presentation provides for common representations of data transfer between applications. And then layer 7 contains protocol used for processes communications. So right now, folks, you're essentially looking at a layer 6 and layer 7 right now as you look at this screen. TCP IP reference model, we kind of saw that. Controls the hardware devices. Internet determines the best path through the network. Transport supports communications between various devices across diverse networks. And then the application, those two are the same, right? Application layer on the OSI model and the application layer on the TCP IP. Represents the data users, encoding, being able to see what we see. Those ones and zeros getting translated into what we can see in our, looking at it on the screen. Here's another graphic here, which is pretty cool, a little model comparison. As you can see here, the TCP IP model, the network access, the network layer of the TCP IP model is equivalent to the physical and the data link layer of the OSI. Now the internet layer 3, they both deal with the same. Those are the same layer. So TCP IP OSI, they see those as the same. Transport layer, kind of the same, right? Being able to transport that data that it needs to get to. And then the presentation, session, and application layer all encapsulates in the application of the TCP IP. Data encapsulation. Segmenting messages. Segmenting is the process of breaking up messages into smaller units. Multiplexing is the process of taking multiple streams of segment data into interleaving them together. Segmenting messages has two primary benefits: to increase speed and to increase efficiency. So, I want to show you this picture here. This is a big computer desk. And if you were to go to Home Depot, or let's say you're online shopping, and you buy this desk, my question to you is, do you think this whole thing is going to show up in one big box? Or do you potentially feel like this may be broken up into sections? Like, for example, you may see maybe this part here will be one box, and then this part here would be another box, and then this part of the desk would be another box. So this would be one of three, this one would be two of three, and this one would be three of three, right? So they'd be broken up. And then when you actually get the box, you'll see the labels on them. One of three, two of three, three of three. You essentially know that that's the sequence that this needs to be put together, right? You need to have these boxes in order for you to have your desk. Very similar to how mail is sent out. Okay, sequencing messages is process of numbering the segments so that the message can be reassembled to its destination. Very good. Reassembled, right? It needs to be reassembled, because if it's not reassembled, you have improper information, like your data won't be there. So imagine, again, going back to this desk, if this was not assembled correctly, the desk would not look correctly, right? So we want to make sure that it gets reassembled like it needs to. So, for example, if you take a look here, it has all the different mail that's going out, 321, and then the mail server actually gets it as 321 as well. So all the information is all the same, right? This is the sender, receiver, all that good stuff there. Protocol data units. Encapsulation is a process where protocols add their information to the data. At each stage of the process, a PDU has a different name to reflect its new functions. So see how it passes down to the stacks. There is no universal naming convention for PDUs in this course. The PDUs are named according to the protocols of the TCP/IP protocol suite. So as you can see here, we have the data stream, the segment, the packet, the frame, and the bit streams. So as those ones and zeros comes into that physical medium, all right, you're sitting here at your computer. Actually, let me get my marker up here. You're sitting here at your machine, and you request something out to the internet. That physical medium is going to be plugged in somewhere on that layer 1 of that OSI, right? And those ones and zeros comes in. But we can't see those ones and zeros. We need to be able to decode that. So these different layers, as they come in, we have our frame trailer, frame header. Notice this is our data. Our data keeps getting passed up the model so we can get to where we need to, so I can see that information. But it has company. It has different protocols that are attached to it in order for it to get up there. So in this example, we have our frame header and our trailer header. And I want you all, let me erase this really quick. I want you to think of this as the front of the train, and this is the caboose. Okay? Front of the train, this is the caboose. So the ones and zeros come in, and we have our train, and then we have the engine, and then we have the caboose carrying all the data. And these items here, these are all the different cars of the train as new protocols come into place. But the end result is to get this data to move all the way up so I can see it, or whoever's asking for that information can actually see the information there. Here's another encapsulation example. The level above does this process and then passes it down to the next level. So each level has a rule. Each protocol is designed to do something. And once again, as it decapsulates, this is kind of what happens, right? Very similar to this, as we discussed. You order this, it gets broken down into 3 different pieces. As soon as it arrives, you open it up, it has instruction manuals, right? So you can kind of reassemble this picture in your living room because you really, really like this desk. It looks really, really cool. Data access. Both the data link and the network layers use addressing to deliver data from the source to destination. Network layer sources and destination addresses are responsible for delivering the IP packet from the original source to the final destination. Remember, original source, the original source to the final destination. That's actually, I don't know if anybody's seen that movie. It's kind of scary. Final Destination. I don't recommend you watch it. If you haven't seen it, sorry, but it is kind of scary. So here's the final destination, as you can see here in Anchorage. And then we have Sun City coming from Arizona. Now, take note. I want you to notice how both of these have 2 different addresses. 2 different addresses. So I'm wondering how this mail can actually get there. We'll kind of get into that. The data link layer, source destination address, is responsible for delivering the data link frame from one network interface card to another NIC on the same network. IP packets contain 2 IP addresses. You have the source IP address and the destination IP address. Source IP address and the destination. These addresses may be on the same network or they might be in a remote session. Now, when we're looking at layer 3, we have what's called the network portion, and then we have what's called the host portion. Network portions, this portion here, I'm just going to write this word on here. The network portion of an IP address, these are static, which means they don't move. And then the host portions, these are dynamic, which means they can fluctuate. The dynamic portions can fluctuate. Excuse me, the host portions can fluctuate. So the network portions are static, which means they don't move. The host portions are dynamic. They can move. So let me give you another representation of that, how that will look on this cul-de-sac here. Let's go back to my cul-de-sac here in my house. Love showing these little graphics. Super cool. All right. So as you can see here in this graphic here, when these homes were built, they were all built on the same street. So that means this street's going to have a street name. Let's just call it Cisco Street. We'll call this Cisco Street. So here's my first question. Is Cisco Street a dynamic street, or is this going to be static? You send me an email, let me know what you think that is. So we have our Cisco Street, okay? Now we have our homes. Now, each one of these homes are probably going to have the same zip code, which is also static. But what makes them dynamic is that they all have different numbers. That's how we can identify them, right? So these are going to have different hosts, the different numbers. So the static portion of this block is going to be, kind of gave you the answer already. It's going to be the Cisco Street, and they're all going to be in the same zip code, right? But the host part, the part that's dynamic, is the different numbers of these homes, the very, very different numbers of those homes. So devices on the same network, and as we just talked about it, when devices are on the same network, the source and destination will have the same number in the same network portion. So in this case, we see a 192.168.1, and then this part here showing this is the host bit. So by looking at this IP address, you may be trying to figure out how is it possible that these are all on the same network. And the way that is, and I will show you briefly, we will get into this in other videos. These all have the same subnet masks, which means they're on a WAC 24. Which means if I looked at my subnet mask, which means they're all in the same zip code, right? All of these devices are in the same, these devices here are in the same zip code. A WAC 24 would signify that the subnet mask is a 255.255.255.0. So because these first 3 octets are on, these are static, which means everything that is within that first 3 octets cannot change. For example, PC1 shows 192.168.1. The FTP server is 192.168.1 as well, but the part that changes are the host bits. That's why you see a 110 here and you see a 9. Here's a 9 and here is a 110. Notice how like I said, these are all on the same subnet. Those are the same, have the same network ID. The role of the data link layer addresses the same IP addresses. When devices are on the same network, the data link frame will use the actual MAC address of the destination. This is kind of like ARP. MAC addresses is basically the physical address of a computer. MAC addresses are physically embedded into Ethernet and are local addressing. The source MAC IP address will be that of the originator link. The destination MAC address will always be on the same, even if the destination changes. So how does it know how to get to? And there is a protocol. We'll write that down. Protocol is called ARP, and it stands for Address Resolution Protocol. It matches IP addresses with MAC addresses. Pretty cool. Devices on a remote network. So what happens when the actual ultimate destination is not on the same local area network and is remote? So if you're somewhere else and you're trying to access the data, or you're trying to access something that's not in your network, how do you get to that? What happens when PC1 tries to reach the web server? Does this impact the network and the data link layers? That's the question. Let's take a look at that. The role of the network layer. When the source and destination have different network portions, this means they are on different networks. That is correct. So they're on different networks. So it says when the source and destination have a different network portion. So that's very similar to this. And you guys know I'm going to show you my lovely envelope. When the source and the destination have a different network portion. So essentially, here's the source. Source is the Miss Jane Doe, 40th Theater Street, Sun. This is on a different network, right? And obviously, Anchorage is on a different network. So this means they're on different networks. So how does it get there? How does it get there? I want you to see these little routers here. Actually, let me speed this. Let me go to a different video here. It's not a video, different slide here. Okay, so the role of the data link layer addresses different IP networks. The default gateway is a router interface IP address that is part of the local area network and will be the door or gateway to other remote locations. Okay, so let's take a look at this graphic here. And obviously we can see, let me pull out my magic pen here. I love my pen. As you can see that this PC1 is on a 192.168.1.110. Okay, that's the IP address. And take note, the router is also on the same subnet, 192.168.1, and it has a host bit of .1, so everything here is a network portion. But you see that these IP addresses are different. These IP addresses are different. So essentially, how does it know to get to this web server? When PC1 sends information to this web client, how does it know that it's in a completely different network? I'll ask you this question. When you mail off something, when you mail off a letter, when this letter gets mailed off, how does the post office know that this city is not in the same city? Easy. So I want you to think of these routers, because it says default gateway, right? The default gateway is the router interface IP address that is part of the local network, will be the door of the gateway. I want you to think of these places here as big post office hubs. And essentially, each one of these routers, they all speak to each other. They all have redundancy. So if information were to hit the switch, which is an intimator device, and it goes out of the gateway, it says, hey, I need to get to the 172.16.1 network because I have a web request. My client wants to get on the web. Right? I need the web request. The local router here says, I have no idea who that is, but I'm going to send that out to somebody I think that may know. So it does. Sends it to another router. Router says, hey, I see you have information coming from the 192.168, and you're looking for somebody that's on the 172.16.1 network. I think I know who that is. I'm going to send it out of my gateway. So it sends it to the next gateway, which is the next little hub, right? And this hub says, hey, I hear you looking for information from 172.16.1. Guess what? That network is a part of my network, and I'm going to send it to the web request. That is a web server on my network. Web server gets it, and then it goes back this way. Sorry for my crazy artistry. And then the person that's at PC1 gets that web request. Folks, the cool thing about this is probably the most fascinating item that I love about networking, is the fact that when you double click on that web request, when this web server is being hosted somewhere that's maybe thousands of miles away from you, the fact that it happens so quickly is absolutely amazing to me. That it hits those multiple routers and it goes out of those different gateways as quick as possible so it can get to that, so that data can get back to your computer. That's one of the beauties of networking. So amazing. The role of the data link layer addresses different IP networks, and we just kind of talked about this. So the data link addressing in local addresses, so it will have source and destination each link. So the MAC addressing is the first segment, and that's signified by all A's. So when you get to all A's, it sends out the information through its all gateway, and it receives a frame. That's kind of what this is. Go back. So as soon as it sends it out the gateway, it sends it out to the MAC addresses, which is associated. This is the physical address associated with the IP address. And then it gets to its web server, and that information comes back. So essentially, one way of trying to figure out how these IP addresses associated with the MAC addresses is essentially the MAC addresses, right? The MAC addresses are associated with the IP addresses. Data link addresses. So since data link addresses is local addressing, it will have a source and destination for each segment or hop of the journey to the destination. So I want you to think of these little hops. And we kind of talked about this in a slide before. These are little post office hubs. Notice how they're all connected to each other. They all have NICs on each other. These are all layer 1 type items. So these are all hops. So when you see the word hops, hop or journey. It's essentially, it's like you're sending data or you send in a box, something UPS ground or something like that. It's probably going to hit multiple stores, multiple hops, multiple routers, things of that nature. So the daily continue. The MAC addressing for the second hop is source. So once again, it's locating the MAC addresses and associating with the IP addresses. Notice that the packet is not modified, but the frame is changed. Therefore, the L3, which is layer 3, IP addressing does not change from segment to segment like layer 2. So as the IP address, as see, here's the original source. This is a person asking for that information as it's going out. The destination and the source NIC, they all stay the same there. I hope you guys enjoyed Module 3. Pretty cool video. Make sure you get your packet tracer downloaded. If you haven't done that at this point, make sure packet tracer is downloaded so you get that extra practice. Until next time, have a good one.